Now that we've talked about systems of linear equations, we have the tools that we can use to actually check whether a given vector is a linear combination of some other vectors. So let's do an example. Is the vector 4, 8, 6 a linear combination of the vectors 4, 5, 6, and 2, 1, 3. So now when I write that, I mean of the set consisting of these two vectors. What we're trying to do is we're trying to ask, are there scalars and to be, what's the word? Well, word about what I'm trying to do. Instead of calling the scalars C1 and C2, I'm going to call them X and Y. So are there scalars X and Y such that X times 4, 5, 6 plus Y times 2, 1, 3 equals 4, 8, 6. We can combine everything to put this into components. Well, the first component is the equation 4x plus 2y equals 4. The second is 5x plus 1 times y equals 8. And the third is 6x plus 3 times y equals 6. So in other words, we're trying to find scalars x and y such that this system of linear equations holds. We're trying to solve this system of linear equations. But really, we don't care what this x and what this y is. We just care whether or not they exist. In other words, is this system consistent? Well, we know how to figure that out. We can use an augmented matrix and do Gaussian elimination. The augmented matrix of this system is 4, 2, 4, 5, 1, 8, 6, 3, 6. One can show using Gaussian elimination. I'm not going to do the steps. So using Gaussian elimination, that this is row equivalent to the row echelon form matrix 1, 1/2, 1, 0, -3, 6, 0, 0, 0, which is consistent. So our original system is consistent, and therefore the answer is yes. But importantly, I want you to notice that the vectors that are in the augmented matrix, this, this, and this, are the vectors that we started with. This vector, this vector, and this vector. So those three vectors are the columns of our augmented matrix, but in a different order. So this guy here is going to be the target one, so that's on the right-hand side of the vertical bar. And then these two are going to be the columns of the coefficient matrix. Our next example is this. Is 4, 8, 8 a linear combination of the vectors 4, 5, 6, and 2, 1, 3. Using the ideas from the previous example, all we need to do is put these two vectors as the columns of our coefficient matrix, and this guy is the right-hand side vector, the guy on the right of the vertical bar. So we have 4, 5, 6, 2, 1, 3, 4, 8, 8. And now we need to ask, is this system consistent? To do that, we can put it into row echelon form. So this is row equivalent to the matrix 1, 1/2, 1, 0, -3, 6, 0, 0, 2. And looking at this, we can see that in this last row, I have zeros over here to the left of the vertical bar, but something not zero to the right of the vertical bar in that same row. And therefore, this is inconsistent. So our answer, therefore, is no. This vector 488 is not a linear combination of these two vectors. In the same way, the same idea generalizes to a way to show that any vector is or is not a linear combination of any set of vectors. And that is our next theorem. This time I'm going to actually write it out because I didn't remember to put it into the computer beforehand. Yay! This is theorem 2.4. A system with augmented matrix A, B is consistent if and only if the vector B is a linear combination of the columns of A.